Well, I want to welcome everyone who's watching or listening or reading the second part of this oral history with Ed Feigenbaum. In the first part, we went pretty much chronologically, starting when you were born and ending with the national service that you did after your retirement from Stanford. Now, today, what I want to go through is sort of cross-cutting topics that go, certain themes that happen throughout those years, and it's easier to organize some parts of your life chronologically and other parts by topics. So it's topics today. And the first thing I wanted it strikes me, if you had to summarize a lot of your career was based on the idea of heuristics and studying heuristics as a great metaphor for doing artificial intelligence research. But what I want to ask you is, what were your own heuristics for the personal choices that you made through your life? So the way it gets through to you, and instead of the scientific, but also the personal.
Don, that's a really good question, and there was a time in my career when I would try to write them down and give students lectures on that as kind of career direction. And those will be, not some, they will all be in the Stanford archives, in the special collection of my stuff. So right now I'm just going to try to spin off a few off the top of my head. Where shall I start? I think I'll start with one that I've talked to you about earlier, which was that I found myself to be a better discoverer than inventor, which meant I needed to pay a lot of attention to empirical data. Because in empirical data, one can discover regularities about the world, which means that my methodology kind of forced me to pay attention really carefully to the real world. So not to move off in fantasy land in science, but to stick pretty close to reality. That was one thing. The other thing was, never move off into a complicated problem area unless you have a problem domain that you can get data from, that you can work very closely with. That led me, I saw it at work when, in my graduate training under Simon and working with Knuth on their chess playing program, or their work on, even when they were doing GPS, they still were using concrete task domains like trigonometric identities. And then I spent years looking for the right task domain for studying the problems that later became, scientific induction problems that later became the Dendral program. That was a key thing throughout my life, was to look very carefully at the problem areas. Some would be terrible. If you wanted to work on a certain kind of problem, some problem domains would be terrible. Some would be extremely good. Knuth, who was always impressed with the Dendral project, but not so much with the brilliance of the ideas in the Dendral project, which he thought were interesting and a good coupling together of other ideas that had been in the field, but with the choice of task domain and the way of exploiting the task domain to get the results. So that's an important heuristic.
Is it easy to give an example of a bad one, of a bad domain?
Yeah. I'll give you one that I really rejected when I was searching for the domain that ended up being mass spectrometry because of Lederberg's suggestion. But a domain that I was looking at for studying induction was to induce the rules of baseball from a long string of specific activities in baseball. It turned out that that just didn't feel right. And one of the things that made it not feel right, and there comes another heuristic, is that I've always wanted to, in doing this, work with people who are genuine experts in that domain. And in the baseball thing, it didn't fit. There were, and what I was trying to induce was the rules of baseball.
You didn't know Dutch Faring. He was a friend of mine, but you knew Josh Lederberg. I mean, Dutch was Stanford's legendary baseball coach. But,
No, I didn't. Another heuristic that I used was how to put this. I really like to meddle in other people's domains of work. I just find it absolutely fascinating, which means that there are large chunks of computer science itself which I'm not interested in exploring, relative to, say, exploring physics like you and I were talking about, or molecular biology, or chemistry, or some other domain. I mean, I got involved with many, many domains, X-ray crystallography, engineering domains. I find it fascinating to open the door into those domains, become a rapid expert, not a real expert, just a sort of a 30-day wonder expert in the domain, and find out about a lot of things.
well, is it that you like the idea of finding a pattern in something complicated, taking something that's organic and messy and bringing some order in?
Yeah, I think that's part of it.
If it's real, if it's already clean, you might not feel attracted to it because you have that you're better off finding out how to deal with the more. I mean, even baseball itself is a good example of something that's that is complicated. Lots of nuances to it, but it doesn't have a structure where you want to deduce something about it. So,
yeah. I'm not sure that I thought it through that carefully, but I think you're right.
So this is like an experimental physicist has a complicated universe to observe and wants to try to see the patterns in that. Is that right? But
Yeah, I think I'm much more like an experimental physicist than I am a theoretical physicist. And a lot of my computer science colleagues, and indeed our students who come from mathematical backgrounds, are much more like theoretical physicists. In fact, I've kind of named a disease that they have, which has gotten popularity because Doug Lennon has used the phrase a lot. It's called physics envy.
Physics envy.
Physics envy. Our friends in computer science have a lot of physics envy.
I see.
And heuristic programming is kind of messy. That's in fact what Polya was trying to tell people back with his books on patterns of plausible inference and how to solve it. Talking to his mathematical colleagues and saying, when you prove a theorem and you get to QED, it's not all that simple. You've done something a lot more messy than that to get there. You've searched a big space. You've discarded lots of avenues in the space. You've used a lot of rules of good guessing to get there. But you just don't want to tell people about the messiness of that. And what I'd like to, so the whole idea of using heuristic methods that was to employ all that, all those armaments, you might say, in the service of pruning these enormous spaces. And
and computer science has characteristic of non-uniformity where a computer program has step 1, step 2, step 3, step 4, while a lot of the pure mathematical things, they have one equation that applies to everything, and you don't have, to a mathematician, the hardest thing is you have a theorem that you have to prove by considering 10 different cases. But in the heuristic kind of work that you're doing, you've got thousands of cases, and still you're interested in finding some paradigms that enable you to deal with these, because they don't just go away. Not everything in the world is uniform. So it's a different, at least I'm sorry, I'm injecting my own.
Yeah.
My own.
Let me give you another example of a heuristic that I was using. And I used it sometimes, and I didn't use it other times, and when I used it, it was successful, and when I didn't, I wasn't so successful. And that is, it takes a while to become really, really good at something. Stick with it. Focus. Persistence on problems is really, not just problems, but a whole research track is really worth it. And switching right in the middle, flitting around from problem to problem isn't such a great idea. The thousands of little intuitions and pieces of the heuristics you gather along the way for dealing with a particular problem area or your part of computer science are enormously valuable in making the next step and choosing next steps that don't waste your time and your students' energy and your own energy. Of course, I violated that by doing a lot of miscellaneous things in my career which defocused from those things, but I enjoyed them and did it anyway.
But you did, yeah. I mean, there are some people who are really good at inventing a theory where it's needed. I'm thinking of Jeff Ullman, for example, and then going to another topic a year later and seeing where another area needs a theory, and so but those are very specialized kind of talent. Now, so you started with mass spectrography, the work on mass spectrograms, and then it went into medicine. Did you ever think of? I've always wanted to know if you ever thought of like bubble chamber and cloud chamber. The things which are somewhat analogous, where you have a lot of data.
There was a particular. The answer is yes, we did, and actually didn't work on that particular problem, but worked on similar ones in medicine. But the reason, the one you mentioned, it was salient, was that SLAC was being built, or had just been built when I got here, and Bill Miller was running the SLAC graphics group, and so we had quite a bit of conversation about that, and it would have been actually a very good problem area. And I'm not exactly sure why we didn't move down in that direction. It's just that I had...
But you never claimed them as artificial intelligence as if they were also working on AI.
See, I think that the problem, I'm just guessing now, but the problem may have been that the physics of the dispersal of the particles in the bubble chamber or cloud chamber was too well known. It wasn't.
It didn't need more funding or more.
Well, so
more
the
AI
field, as Nils Nilsson and others have said over the years, and Roger Schank, kind of breaks down between the neats and the scruffies. And
the what?
The neats and the scruffies.
Neat and scruffy, okay.
McCarthy represents the neats.
Okay.
And over the years, Newell and Simon and Minsky and myself and Schank and others represented the scruffies, where we don't insist on a lot of formal clarity in the models. Well, in the case of the bubble and spark chamber photos, there was just a lot of formal clarity there, period.
Mm-hmm.
You didn't really need, but in medicine there wasn't, so it was kind of a good area.
Yeah, okay. But there was more of a need for it that you could see in Already there were
But I've
there
got to
were
say,
zillion physicists working on it.
but I think that what I just said overstates the case in the following way, that, and again, it's a heuristic in life.
Yeah.
Meet a wonderful collaborator, and in this case it was Joshua Lederberg. Meet a wonderful collaborator and really work with that collaborator on some meaningful problems. Lederberg and I worked on a whole chain of problems, and then even when it wasn't directly in our field, we were involved with that, like in diagnostic medicine, or Josh in on the engineering side of what we were doing. That's a valuable heuristic. Another way to put it is that, as we discussed in your oral history, you said you were pretty much of a loner, that you like to work. You gave some examples of where you weren't, but you said most of the time you like to work by yourself. And in one of my heuristics is liking to work with a small number of very smart other people, like Carl Gerasi or Josh Lederberg, or...
Well, that actually was a good segue to the next thing I wanted to ask you was different gurus, but I guess it's the word guru isn't right. I mean, you mentioned Herb Simon many times last time, and he was definitely a guru for you. But also, I mean, as an advisor, I found I couldn't work with my own PhD advisor on a same level, somehow. But with Lederberg, you were more of a team. Is that what you, or would you describe other gurus in your life, or
Yeah, sure.
other?
Sure. Great question. And in fact, in trying to myself structure my past in a reflective way, perhaps in that which might lead to an autobiography, I've thought of structuring it in terms of people. I've worked with, and people who have influenced me and people I have influenced. I think, so no question that the two biggest influences on the way I think were Herb Simon and Joshua Lederberg. Simon's influence was absolutely fundamental in two things: getting me interested in the breadth of the world's problems and not being too concerned with the formal details of the analysis of it. That's why I said earlier, I think in my last session in the interview, that I thought of AI more as a behavioral science than as a mathematical science. That kind of came from Herb's breadth.
Okay. Now, with Josh, did you go to him, or did he come to you?
No, I'll tell you exactly how it happened. Well, if I had a copy here of the book Computers and Thought, I would read you a paragraph at the end of the introduction to Computers and Thought, which gives you my projection, or my statement about what I thought was the fundamental importance of the problem of induction. Mm-hmm. And the more I thought, and so I was looking for a problem domain with which to work. It wasn't an intense problem, because I happened to be, at that time, for reasons that are historical, I happened to be teaching in a school of business administration where I didn't have any great graduate students anyway, so it wasn't a pressing problem. But so it took a lot of thought, and in the middle of 1964, I was invited to a series of Saturday morning seminars, workshops, at the Center for Advanced Study in the Behavioral Sciences, which is on the hill behind Stanford. Carl Pribram was running that. Carl was a neuropsychologist who had participated in writing an early book on information processing psychology, what we now would call cognitive science. The book was called Plans and the Structure of Behavior, Miller, Galanter, and Pribram. So Carl was really involved in that field. He was running this workshop on what amounts to models of minds, whether they were artificial minds or natural minds. And Josh had gotten interested, I should say, re-interested in computing. He had been interested in computing at an early stage of his great career. But then he put it aside because he had other things to do in the fabulous work he did that won him the Nobel Prize. But he got back to it in roughly 1964, taking a course from George Forsyth in Algol and using a problem related to organic chemistry as his test domain for testing out his understanding of these Algol ideas. So Josh knew McCarthy. He was interested in the subject, and he showed up at this Saturday meeting, and that's when I met Josh. So as soon as I talked to him about my interests, he immediately had suggestions to make, and one of them was concerning mass spectrometry. He was working on it in relation to putting a planet probe on Mars, looking for signs of life precursor molecules. And the idea of just beaming the data back to Earth for humans to analyze didn't appeal to him.
I see.
Put the software on board and let the planet probe tell you what the structures of the molecules were. So when I got to, that was since '64, when I actually showed up at Stanford, aside from saying hello to Forsyth and McCarthy, the first person I looked up was Lederberg. And the collaboration began almost immediately. He remembered our conversation. I remembered our conversation. It seemed like the right thing to do. We just fell into it.
This was before he had a Nobel Prize?
No, he won the Nobel Prize in 1959,
I see.
I believe it was. And then he gave all of his Nobel Prize speeches and all that, finally got sick of traveling and decided to look for another field to work in, and he got interested in computing and artificial intelligence.
So he won the Nobel Prize, he's in his 20s, 30, he's
Very
pretty
young,
Yeah.
very young
Okay.
person, yeah.
So you told me a story once about his stack.
Oh, yeah,
is that-
so, sure, I'll repeat that. Josh, I know if you're listening, this is my interpretation, and you don't have to buy this at all. I just saw Lederberg yesterday in New York, and he said he was interested in hearing this oral history. But I was trying to, let me start this again. One of the questions that I and others had been looking at during the 60s and a little bit later in the 70s, Herb Simon was the leader of this. I was more of an AI engineer, you might say, and he was more of a psychologist. But the question was, what is it that distinguishes experts from novices? Herb did some experiments and came up with some ideas. I was asking the same question of myself when I would watch Josh Lederberg at work. When I would watch his mind at work, or listen to his mind at work. What is it that makes Josh so amazing, so penetrating, so deep, looking into problems? And knowing what I knew about problem solving, I made a conjecture, which is that the portion of Josh's immediate memory which serves as a place to return to subproblems was just a lot bigger and more efficient than the rest of us. He could keep a deeper stack of it. Maybe I should say it another way for the people watching this oral history. One of the key techniques that AI people, the models that AI people use of problem solving is what's called subproblem reduction. You divide and conquer. You don't solve a big problem all at once. You solve it by dividing it up into subproblems, which you divide into subproblems, and you have to keep track of that whole chain of what we call the subproblem hierarchy. And Josh just had an amazing way of keeping track of where he was in a deep line of thought. Mm-hmm. And my feeling is that can be as genetic as any other thing. It can be as, I mean, I don't think of myself as being able to run a 100-yard dash fast or a 4-minute mile or anything like that, because I don't have the musculature to do that. Mm-hmm. There's some things that are just genetic, and maybe Josh's deep stack is something that's genetic, or maybe he figured out how to train himself to do that when he was young.
I was thinking, it came up in the other interview too, where we're talking about levels of abstraction, and it's very similar. that you have to know the state of lots of different things at different levels. Yeah, that's.
Don, it's another thing that comes up, you mentioned it in your interviews, is the level of concentration you need to do that. You
Yeah.
can't be interspersing other symbols with that stack
Yeah.
when you're doing it.
Yeah.
It's too hard to do both at the same time. I guess the lesson for kids out there watching this interview is don't listen to a lot of music while you're doing complicated things, because those are just other symbols which are coming in there and bothering your stack.
Yeah, right. You can listen to baseball games, though, sometimes it helps. And I'm just kidding.
Yeah.
But since baseball came up, when you're doing something boring, some kind of distractions do help. But when you're doing the science, the interruptions are killers.
Killers,
Because they
right,
destroy the-
absolutely.
Yeah.
Yeah, and so therefore you find people like, people who take deanships saying, one of our former deans at Stanford said, I remember when he took the deanship, yeah, that's okay, I can do that part-time and the rest I'll run my laboratory.
Yeah.
Well, there's no way you can run your laboratory when you're doing that. You just lose it.
Yeah, okay. Now, so, any other gurus or?
Yeah, I think, so Gerasi was another one. Gerasi, the way Josh and I got Gerasi involved, so let me tell you a little bit about Carl Gerasi. He's a brilliant person. Lederberg once called him when I heard Lederberg call him a phenomenon of nature.
Well, I was once having lunch with Josh, and I remember exclaiming, Josh, how could you have ever evolved? Okay, but anyway.
Yeah, that's right. Remind me to come back to that question, that
okay.
exact thing you just said.
Okay.
Because I want to make a comment about that.
Okay.
That's another heuristic, actually, of
Yeah.
of my life and career. But anyway, Gerasi was the so-called father of the birth control pill.
Yeah.
He then went on to run Syntax Corporation. Actually, his whole career at Stanford was spent 50% being a professor, 50% running a company like Syntax or one of his later companies at Stanford. He was a collector of, one of the world's great collectors of Paul Klee paintings, and just a very broad intellect. But when we got to know him, he was a mass spectrometrist, one of the best. And he had a laboratory over in the chemistry building. And Josh said, by 1996 somewhere, like 1 year into our project, Josh said, look, Ed, we're running out of what I know about mass spectrometry. So in order to make any progress, we're going to have to get someone who really knows this. Let's get Carl. So the trick, we had a little strategy, which worked. We took Carl up to the Stanford AI lab where our program was running under time sharing on McCarthy's machine. And we showed him the program working on, well, first we showed him the good stuff, which was working on some amino acids spectra. And then we showed him the program running on alcohol spectra. And it was doing a terrible job, even though alcohols are much simpler. But it didn't know anything about alcohol mass spectrometry. So it was doing a terrible job. And Carl said, that's terrible. And we said, yeah, that's right, Carl. Now, what is it that you know about alcohols that our program doesn't know? And that got Carl hooked. And from then on in, it was just Carl and his team supplying that kind of knowledge. And then we had a program of research that Carl laid out that extended the range of Dendrol's abilities. Each time that we went into something more complicated, we had to do more complicated stuff in the program. Like at one point, we went into ring structures, which means that we had to get Harold Brown in he came from Ohio State to help, and some other people, Larry Mazinter, to help figure out the, and we consulted with you and we consulted with Bob Targent about understanding the graph theory of the ring structures and getting that into a program. So Carl was a big influence on what we did. Then I would say another it was a person I influenced a great deal, but he also influenced me a great deal, and that was Bruce Buchanan.
I was just,
Bruce-
just guessing that was
I
going to be.
found Bruce, luckily, stroke of sheer luck. Bruce was a graduate student in philosophy of science at Michigan State. He applied for a summer job at Rand. I was working in the summers at Rand at that point. Paul Armour, who was hiring people, gave me this application and said, Ed, would you like this person for the summer? And it was just when I was thinking about scientific induction. The reason being that Josh's comments had turned me in that direction, that scientists were, it was just a natural to use scientists to study induction because they were professional inducers. That was their job, to look at a lot of data and construct hypotheses and theories. So Bruce came along with this thesis he was writing called Logics of Scientific Discovery. Listen to those words, logics of scientific discovery. That was exactly, I mean, it couldn't have been more tailor-made. So Bruce came in the summer, and then when he wanted to get a job as an assistant professor of philosophy somewhere, he asked me to write a letter for him, and I just said, Bruce, you don't want to do that. What you want to do is come and work with us. And I told him what the project was, and he did. And over the years, it was a really great collaboration. Bruce had just the right flavor of insight from his background in philosophy and his work in computer science to contribute to our work. So that was excellent.
Is there, I don't know how to ask this so that you can answer modestly, but other people who would put you on their list of gurus?
Yeah, so I think, yes, the answer is, and a lot of them showed up at the 70th
Right.
birthday fest.
that we
It
had.
wasn't kind of a shrift, it was
Yeah.
just fest.
Well, we call
But
it.
Doug Leonard is one of them.
Yeah,
His graduate student career was kind of languishing under Cordell Green. It wasn't getting anywhere, and he somehow discovered me and described what he wanted to do. It fit exactly what we wanted to do. He just went straight ahead. That was his AM
the AM.
thesis.
Yeah.
And we've had a very good collaboration over the years. Another one is Randy Davis.
Randy Davis.
With Randy's work on
Yeah.
explanation.
Yeah, I see. And
I mean, I don't know exactly who would,
I don't know, Peter.
but
Friedland?
there are many,
What, I'm thinking Peter Friedland maybe, or.
oh, Peter as well, sure, sure. Peter and Mark Stefik did wonderful theses. Well, there's a whole story there about the so-called Malgen project, molecular genetics. It was the first project in which computer science methods were applied to what is now called computational molecular biology. And the reason we were able to get in there early is that we had Joshua Lederberg as our collaborator. The genetic engineering methods had just been invented by Stan Cohen and Herb Boyer, and Stan Cohen was one of the co-PIs of one of the projects in our lab, of the Meissen project. And so we were there very early. And we also we were masters of a computer language that was way better at handling symbols than it was at handling numbers, namely Lisp. So, but that's what their domain was. It was all symbols. So we were able to give them tools, they were able to give us insights. And Peter and Mark did the first two theses on using AI methods for experiment planning in molecular biology.
Yeah, you had the vocabulary and the kind of theory that was needed to talk about this kind of modeling.
Yeah.
Yeah.
That's right.
What about, okay, I'm thinking Doug Brutlag, was he involved with this? Maybe I was
Wait,
wrong.
say it louder.
Brutlag.
Oh, Doug Brutlag. Okay, so here we were working in molecular genetics, molecular biology, and we had Josh, but Josh was at that time getting to be quite a public figure, writing columns for the Washington Post, and eventually 2 years later becoming president of Rockefeller University. And we needed a more hands-on molecular biologist who was able to work with us on a day-to-day basis. So we recruited two of them with help from others. I don't know who helped us get them, but Doug Brutlag was one of them. He was in Paul Berg's department in molecular biology. And Larry Keddes in the medical school, K-E-D-E-S, was a hematologist who was interested in molecular genetics at the time and was really interested in computational methods. So Doug and Larry were our domain experts, and Peter and Mark were the AI students, and I was kind of the AI and computer science glue for all of that. Then later on, when the product of our work turned out to have a very broad applicability because the field was exploding late in the 70s, exploding from a few people to hundreds of people who were interested in doing this. The software got to be very widespread. First on a NIH-supported time-sharing machine at the medical school, and connected to what was then the ARPANET, and later in the basis of a company called Intelligenetics that was started by myself and Peter and Doug and Larry.
I want to go into companies later, but
Yeah.
right. But I guess now would be a good time to just ask about SUMEX and ACME.
Yeah, good point. In fact, Josh and I yesterday were just talking about the history of all that. Okay, so in 1965, there was a confluence of events in computing occurring, besides the formation of the computer science department, which occupied the mind of George Forsyth very much in early 1965. There was a confluence of other computing events going on. Basically, a new generation of computing was arriving on the scene in the form of either the IBM 360 set of machines for some people, or the CDC 6400, 6600 set of machines. And even at the time, the original PDP-6 was showing up at that time. It wasn't as powerful as some of those other machines, but it was a very flexible, beautiful architecture machine.
This was the first, well, I don't know, silicon revolution or some way. I mean,
Yeah,
some way, the
that's right.
transistor.
Yeah, solid logic is what IBM called it.
Yeah, solid state, yeah.
So it was time to augment the computing capacity of the Stanford Computer Center. It had a Burroughs machine. It was going to get something else. I mean, it could maybe get another Burroughs machine, or it could get something else. And George didn't want to handle that. He had his hands full with the computer science department. So he asked me if I wanted to basically run the computer center and handle that. But it turned out that Bill Miller had arrived at Stanford, same day I arrived, January 1st, 1965, as another faculty member in our department. And Bill needed to do the same thing for the SLAC. He was brought in to do that for SLAC. And they needed a massive machine. So it looked like we ought to do whatever we did together, because software was a big cost. Software was a big pain in the mind, pain in the neck, and we better do it together, and then we can master one operating system and not two different ones. Well, so we decided to do that, and then Josh Lederberg had the idea that he wanted to bring computing to the medical school, and why didn't we, A, go out and get some money to do that from NIH, and B, join it in with this other plan. So that's just what we did. We had a plan to, it ended up, I won't go through the gory details of how we ended up this way, but it ended up being a 360 mid-sized machine, originally slated to be a Model 67, but that was never delivered, so it was a Model 65. A Model 91 for SLAC, which was a very fast machine, and a Model 50 for the medical school machine, picked partly because it fit our budget, but partly because it was a machine that IBM was selling a, would you believe this? I don't know exactly what they called it, but my word would be a mega memory. Namely, you could buy 1 megabyte of memory amazing, 1 megabyte.
Yeah.
You could get 1 megabyte of main memory, which means you could write a memory-based time-sharing system without a lot of swapping.
Yeah.
If you kept, imagine you had 1 megabyte to do it
I
in.
can't imagine. I had, 10K from.
Yeah, right, exactly.
Yeah.
So we bought a 360/50 with this big memory, so-called big memory. And on that, and I hired a friend of mine from Berkeley, Gio Wiederhold, to run that facility and develop that time-sharing system. That was called the ACME system.
Okay.
I think it was ACME stood for I'm not positive of this, but it was something like a computer for medical education or something like that.
Wonderful, okay.
Something like that. And then,
And that was different from SUMEX.
now, okay, ACME, so ACME was a time-sharing system for the medical school, not just for our AI research. It was
Okay.
in
Right.
fact, for our AI research, it wasn't all that good because it didn't have well-developed Lisps on it.
Right.
And so we were using McCarthy's ARPA-supported PDP-6 and the
PDP-6.
PDP-10. But then our projects really grew up. Dendral was very successful. We moved into medical diagnosis and a couple other medical-related projects. So it looked like it was time for us to get, basically for us to do what McCarthy had done up at his lab, but to do it for our own lab. We were on campus, not up in the foothills, largely actually, because we were collaborating with experts on campus, and driving up to that facility was a big pain. We needed them when we needed them. We didn't,
Right.
took a half hour to get around campus and up on Arastadero Road so Josh and I applied for some money from NIH for a machine like McCarthy's, but using the 10X operating system rather than the one that they were using at Sale. Let me talk about Licklider a minute.
Good, yeah.
Licklider had come back to DARPA for his second time around. He was the guy who sponsored McCarthy in the first place at Stanford and sponsored me at Berkeley in the first place. But he had come back to DARPA for a second round, and Josh and I, and of course we had been involved, my group had been involved with DARPA PI meetings and the growth of the ARPANET at the beginning, and we asked Licklider if we could attach a non-DoD machine to the ARPANET, namely an NIH-sponsored machine. And he said, of course. So we got ourselves an IMP, I believe it was at the
Right.
time, and
Message
attached
processing.
ourselves to the ARPANET, and that suddenly,
What year are we talking about?
like roughly 1973,
Oh, okay, so this is.
something like that.
I see, so.
Licklider came back in 73, I think.
Oh, okay. So then, was this the only non-DoD machine at the time? you
At the
think?
time, it was the only non-DoD machine. But that suddenly opened up the prospect that the stuff we were doing, to be more specific, the software we were developing in our group could be made easily available to a national community of researchers wanting to do AI in medicine. That became the acronym AIM. AI in medicine was the national group.
Oh.
SUMEX was,
SUMEX-AIM.
yeah, and SUMEX was the Stanford University Medical Experimental System, AIM, the Artificial Intelligence in Medicine National Group.
Do you remember what the internet, I mean, how many different operating systems were there? You say you have 10X on this one, and McCarthy had his, I don't know, what it was.
Homebrew. Yeah.
Homebrew weights, and then there was ITS at MIT, the Internet Incompatible Time Sharing.
Yeah.
I suppose there were quite a few different ones then.
Yeah,
Okay, that's not-
maybe every machine had it.
Yeah, okay.
No, 10X was, eventually 10X kind of took over on the DEC machines, but
Yeah, but anyway.
Anyway.
It's good that the internet actually started in this, with all these different kinds of machines, because that made it more likely that it would be useful in the future.
well, and I think they had that in mind from the very beginning.
Yeah, okay.
So then we hired Tom Rinfleisch from Caltech, a real expert who just ran that facility for us, did a superb job over a 20-year period.
And was this used by people all over the country then?
all over the country. In fact, when I was the software I was telling you about before for Malgen, when we provided a tool for sequence analysis, which is now common. Now it's, everybody does sequence analysis, but it was just us and a little biology group in Wisconsin, I think, that had developed software for it. We had 300 users of that coming in over tips, not IMPs, but coming in over tips located all around the country. Remember, ARPA had put in modems on computers called tips.
Right.
So we had a big user community.
It's an IMPS. Yeah, it's like I was using Maxima at MIT at that time. So it was a similar thing. People from MIT would log into SUMEX, or people from Wisconsin. So,
Yeah.
Right, okay, good.
Well, or
Yeah.
Saul Ameral's group at
Right.
Rutgers
Yeah.
was another example, Carnegie Mellon
Yeah.
people.
Okay, good. Now, let's see, going, I don't know if I should try to go smoothly through all these topics, or, yeah, let's talk about companies now.
Wait, Don, can I just back
yeah.
up a second and say one more thing about SUMEX?
Yeah,
SUMEX is in danger of being sort of bypassed by history, in the
well,
sense that Tom, who is now retired, hasn't, I don't think he's had an oral history here, and I don't think the history of SUMEX has been written, but someone ought to go back and do it. There are some absolutely brilliant things that happened at this medical computer facility. For example, the Computer History Museum shortly will have an exhibit in which they're exhibiting the history of the first router that was done at SUMEX. And it wasn't done by Cisco. No matter what Cisco, the founders of Cisco claim, that stuff was taken from what Bill Yeager did. And the Computer History Museum is cleaning up that piece of history. But there's a lot of other stuff that someone ought to go back and do that history sometime.
so the archives from McCarthy's computer, all the DART tapes, all the backup tapes have been preserved. Is there a similar thing for
Yeah,
SUMEX, for people
yes
to
and
actually
no.
look at the data?
Tom Rinfly saved 1,300 dump tapes when SUMEX went out of existence. And he saved 2 tape readers. And he's using a PC-based simulator of what the machine used to be. But on the other hand, Tom's pretty busy doing other things. So there's no
It hasn't been
There's
lost
no
yet.
group, there's no volunteer group that's helping Tom preserve the history of SUMEX. He did give Lederberg and me what amounts to the email of SUMEX from the time we got online to about 1980, 1979.
Email, okay, yeah.
But then there's all the files in the directories, and there's a whole history there.
Yeah, well, this is, I guess I should talk a little bit about history then, since we're in that, and I'm trying to segue through my question.
Yeah, sure.
And so you should show everybody the tie you're wearing. It's a core memory tie.
Yeah.
I don't know if it's possible to zoom in on that. But tell me
It's
the
from the
story.
Computer History Museum, actually from the Computer
Oh,
Museum in Boston.
Yeah.
Gwen and Gordon Bell gave me this tie once, and it's a representation on the tie of the wires and the cores that used to go into core memory.
I just wanted to, I mean, in general, you've got this great interest in history and preservation, and I wondered if this is late in life, or if you had this all the way through, or if you were, if you loved history when you were younger, the same as you do now. What are your thoughts about these things? I know there's also talk about semantic web, which we can get into too.
Yeah.
Okay.
When I was younger, I was too busy for history and not cognizant of the importance of it. I hadn't lived long enough to understand the importance of it. Even though history as a subject was okay, it wasn't, I mean, there's nothing I disliked about it, but it wasn't like I had this lust to be a historian and accidentally ended up a computer scientist. But after I interacted with Josh Lederberg for several years, he taught me the importance and value of saving documents and annotating them and putting metadata on them, making sure they were organized and they were sure to be valuable someday. And I began to understand that myself as I saw ideas unfolding and influences on those ideas unfolding. And as I got older and began to see my own career unfolding and began to realize the impact of the ideas of others on my ideas. So I became more and more of a historical buff. Then, Lederberg and the National Library of Medicine collaborated on the first of what became a series of websites on the National Library of Medicine computer called Profiles of Science. And that convinced me to get very serious about, well, I was semi-serious about the archives. I spent a lot of time on the Feigenbaum archives in 1985 with Henry Lowood and setting up this collection at Stanford. But more recently did a second accession and became interested in the digitization of them, the organization of that digitization so that it would be meaningful to historians, curators, scholars, 50 and 100 years from now who were interested in the flow of ideas around this time. I mean, look how many people are interested in the flow of ideas around Newton's time, Newton and Leibniz and the calculus. And
I was reading last night about Darwin. I suppose I don't know. It's not as well known as it should be, but he was in poor health throughout most of his life, and he referred to this all the time in letters that he wrote and so on. So there's a wonderful article that just came out by two doctors in Chile diagnosing his medical problems, but it also fits in with all of his life very perfectly, and without this kind of documentation, so much bad conjectures would be flourishing, and now we know a lot more about the way important things were discovered because of
So Don, another way to look at it would be to say that to go back to the very first question you asked me today, if you're interested in discoveries and the history of ideas and how to manufacture ideas by computer, you got to treat this as data. This is data. This is fundamental data. How did people think about what was out in the environment? What alternatives were being considered? Why was the movement from one idea to another idea seen as preposterous at one time and accepted at another time?
And you're working now on some kind of facilitating automatic processing of this data.
Yeah, I'll tell you about it a little bit, but I always like to talk about things that have been done and are, someone can, in the future I want one of these scholars to be able to say, yes, he talked about that and here's the program, or here's a representation of it. This is just a conjecture. We're working with the Stanford Library. I am working with the Stanford Library on trying to do at least a semi-automatization or at least a very significant facilitation of the kind of work that the National Library of Medicine did with Lederberg to create this superb historical digitized website. And I'd like to, and what do I mean specifically by it? I mean that everyone who is a professor emeritus, we're going to start with computer science because that's closest into what I know about, but and I'm going to hopefully get McCarthy involved with it, and maybe yourself, other people in computer science, but I'd like to be able to do it in other fields as well. To give every professor emeritus a kind of a workstation, a history workstation, where they have a computer and some software and a scanner and the help of a library archivist to get them started with metadata and get them started with layering on some additional concepts from their field, which the buzzword in AI, which I don't like, is really ontology, but lay on some ontology things, and then maybe a graduate student or two will add some inference methods on top of that and be able to allow a scholar to draw conclusions from what's in the digital archive, as well as just gather data from the digital archive.
Yeah, we have to find a graduate student who also appreciates history at that point in their
No,
life.
this has been a hard problem. We've been looking around. We've finally found an undergraduate at computer science who's doing a minor in history, but it's going to be just as hard as finding a graduate student who is interested in chemistry.
Well, it turned out that last year was the 300th anniversary of Leonard Euler's life, and 2 graduate students at Dartmouth got the history bug, and they went through and they have set up website now, but they digitized, 880 Euler's 880 papers and his correspondence in there, and they wrote a description of how they just love this work. So once you can get them started on it, there's hope, I think.
Now, can you imagine what that would be like if Euler were alive,
Yeah.
and you could actually get audio clips from what Euler thought about some of those documents and how he got these ideas and who influenced him? And
Well, of course, he's one of my heroes, and I'm afraid that I don't want to be disappointed either. But,
well, yeah, that's like Newton. Newton wasn't a real good guy, but
yeah, no, apparently you smoked like a chimney. Okay, so, okay, great. I think we can only hope that people who are watching this now will see that they should also do the same then for the history of their time as we're trying to do now with the new tools that'll be available by then. Now, I guess I really want to ask us the most cross-cutting question of all. I might as well get to it now. It's sort of what things make you the most happy? This is a hard one, but just if you had to, if you sort of look at your whole life and saying, these were the happiest times. So what are the?
yeah.
I don't like top 10 questions usually, but
Yeah.
What does this trigger in your
Yeah.
mind when I ask them?
Great question. Great question. So, I don't know if I'll get the order exactly right, and if I
No.
don't, I'll edit it in
Edit
the
it later.
transcript. But
Right.
the number one thing of all is my wife, Penny. It's a wonderful person to be with. The period of time after we met and got married was one of the most productive times in my life because it was one of the most bubbly, happy times, and it's sort of continued that way throughout life. So that is the number one thing that makes me happy.
Mm-hmm.
And the number two thing that makes me happy are those 4 wonderful girls we have, and now all the grandchildren coming, and they're terrific, and we love to, the girls all turned out to be wonderful and productive and happy, and you know what?
Okay.
I hate to tell this story in a world in which lots of bad things happen to people, but none of those happen to us, and we get together routinely as a family. Not all the time, but at least once a year we all get together, and then subsets, and that made me very happy. Has made me very happy, and continues to make me very happy. Third thing is relationships with a small number of superb people that I've had that continue on. Herb Simon is dead now, but right up until, I didn't know Herb was dying at the time. He didn't tell me that he had a cancer and he was dying, but I would go routinely to Pittsburgh to see Herb. Up until the very end when Al Newell died, I was in close contact with Alan. Yesterday, I happened to be on the East Coast this week, and it was essential that, in my mind, that I go and see Josh Lederberg at his place. He's not feeling so well these days, and I went and we talked a lot about not only the past, but also is there anything we could still do together? Those things are very, and not just with older people too, like getting together with Doug Leonard is always a great pleasure for me, or Mark Stefik, or Peter Friedland, or people like that, Randy, Ted Shortliff, Bruce Buchanan I see fairly often because I make a point of it. I really want to see Bruce. So that makes me happy. Then another thing that makes me happy is, I mean, those are the people things, and the people things are more important than the...
That's right, but we can talk about different orthogonal dimensions.
Yeah, and so the other thing is...
it doesn't have to be a linear order.
Yeah, maybe it's not a linear order, but it makes me very happy to have the feeling that I got to understand very well and could explain a very hard problem, which is the problem of what is it that makes something or someone intelligent. And I don't understand everything about it, nor does anyone else in AI, nor have they ever, but they will eventually. But I know enough about it now to feel very good about where we got to in that. And so that means that it wasn't all dribs and drabs, and it wasn't all a waste. And it means that I have some ways of answering the question what to do next, because things have worked out in the past, and therefore it's a reasonable extrapolation that if you follow that track, it will work out in the future. So I like that. That makes me very happy.
Okay, so you in other words, you gained some answers to questions that you were trying to look at, and in the process you also gained many friends and who shared you know, the journey and so on.
Wait, John, Don, I wanted
Yeah.
to mention one other thing. Two other things. Number one, I never gave up this idea of wanting to plow into somebody else's field. And so the physics you and I were talking about today, that's another example, where it's just a hobby of wanting to find out what the latest is in quantum cosmology and in theories of gravity and so on. And then finally, and not just that, but it's sort of everywhere. I took along with me on this trip to New York, I took along Lee Smolin's book, The Trouble with Physics, which is a very well-reasoned examination of what's going on there. And I also took along Shakespeare's Henry VI, Part 1. That's the kind of, and then
Okay,
the last
that
thing
makes
is,
you happy.
the last thing is my music. Singing with the Stanford Chorus is just, when I do it, there's nothing in the world that's making me happier than that.
Right, that was one of the things on my list, and I know you've done this for a long time. Can you say, I mean, you were, I know you might have introduced me to Harold Schmidt ages ago, but so you've been with the Stanford Chorus maybe from the 60s, or?
Well, so in 1970, in the late 60s, I tried to look for other things to do besides doing the normal thing I would do. The nerdy thing of taking homework with me at night and finishing it up and preparing for my class and going back and teaching it the next day. I wanted to do other things. And one day I saw an ad in the Stanford Daily, student newspaper, for those of you who are 50 years from now watching this. Basses and tenors needed for Beethoven's Ninth Symphony. Well, Stanford Chorus, Harold Schmidt, conductor. I didn't know anything about singing, but I knew Beethoven's Ninth inside and out. I knew it almost by heart, just having listened to a lot of class, listened to it a lot. So I went over to Harold Schmidt and said I wanted to do, here's the ad, and I wanted to do it, but if he auditioned me, I'd never make it because I had no experience in singing. He said, okay, just go sit in the back of the room and see how it goes. That was 1970, and I've never left. Still in the back, still there, still doing things with the Stanford Chorus. Beethoven's Ninth, of course, was done many times, and I even sought out performing it twice with Japanese choruses in 2005 when they do a lot of Beethoven's Ninth in the month of December, which they treat like we treat Handel's Messiah.
Yeah.
And I sang that, and we do routinely, I don't do 3 things a year anymore at Stanford, but usually 1 thing a year at Stanford, and then I find things elsewhere, like next year Stanford's going to take the chorus to Beijing to sing Carmina Burana at a music festival preceding the Olympics. Or I joined up with the Berkshire Festival Chorus and sang Rossini Stabat Mater and a Puccini Mass at Canterbury Cathedral, or singing the Verdi Requiem with the Stanford Orchestra and Australian choruses in the Sydney Opera House, just for kicks, and it makes me feel wonderful.
That's good. That's great. Another thing, I remember one time you came to my house and we had we sang Schubert lieders. I mean, Harold Schmidt was there, and I played the piano. Okay, so now another thing I wanted to bring out is that you've always liked gadgets, as far as I know. You were the first on your block to get stuff, and I mean, when we talked when I was working on a little 8-bit computer in 1980. You said, yeah, you've been playing around with I don't know, Altairs or whatever, things like this, and this is fun again to program this way. And I mean, you were the first person I knew to have a CB radio, and you were Fig Tree was your moniker, as I recall, and so on. You have a Bluetooth hearing aid now. So has this been through your life, and is this a cross-cutting thing, would you say?
So it's getting worse, Don.
Yeah.
Now that I'm retired and I have a lot more time than I had before, I'm getting geekier and geekier.
Yeah.
So I get to, for example, I shouldn't be diving down into the details of the Mac operating system, but I'm using a lot of Macs. My wife is using Macs, and things happen, and you just got to know about them. And
so I can call on you the next time I have.
Yeah, well, if you have a Mac.
Yeah. Oh, yeah.
But I should be hiring someone to do this. But I love the geekiness of it, and part of it is back to when I was. It feels like I'm 9 years old and 10 years old again, and proving Euclidean theorems in Euclidean geometry, where it just felt so good to finally find the answer. You didn't know what you were doing, and then you kind of figured it out, and then you prove the theorem, and it works. And getting back involved with details of computing has that 9 and 10-year-old feeling about it. It really feels good to kind of figure it all out.
Do you think that we're hiding too much of that from people now? I mean, the kids don't have a chance to do this as much as you and I did when we were young. Maybe not.
I'm not sure about that, because we may be hiding that level of it in computing, but everywhere you turn, the levels are showing up somewhere else. Like they may have the same problem they may have geeky issues with their music, the digital music that they generate, and the MIDI channels and all that.
I'm sort of reacting to. Yesterday, I was reading the abstracts of a lot of new books that have just come out, and they all seem to be how to use somebody else's library of routines, and how to learn this language or this other one, and reuse software instead of write your own software, and so on. And it's certainly important to be able to reuse stuff, but it seems to be that if your whole life is just to be reusing, it's not much of a life. I'm reacting a little bit to trying to think of how to put more fun into what computer scientists, people who are hired now as specialists in information theory are supposed to do. or I guess developers is another word for it. And it seems that you can't do the geeky stuff as well, but I'm not sure if you have any similar.
Well, I just think there may be some combinatorics here. That is, what we're doing is packaging up things at this level and saying, these are tools for you to use for being creative at the next level and the next level up.
Okay.
And maybe they are being that creative and we don't know it because we're
Okay.
in our 60s and 70s.
Yep, this is true. I can feel myself getting grumpier by the moment. I mean, so. Good. Now,
Don, I just want to make one comment, though, that is another heuristic that from what you just said, and I know you feel strongly about this because I saw it when you were doing tech and Metafont. People pay way too little attention to the user interface. They're too geeky in the details, and they're not paying enough attention to the human use of these tools and how to make it beautiful. Beautiful is wonderful, and when you see something ugly, it's really offensive, and a lot of the software interfaces that people use are just truly ugly, and I don't know how you can get this across to computer science people. We try a little bit in our department, but we just can't get it across, and maybe it needs something like David Kelly's new Design Institute to do it.
but you use a Macintosh,
Yeah.
which is not ugly. I mean, you presumably enjoy.
It's good,
to a
not
certain
excellent.
extent. Yeah. Okay. I mean, I like.
I mean, there are serious issues with it, and
Yeah.
I'm sure that they know it.
Yeah.
But at least they attend to those issues. And maybe they get 80% of them right, but what do you do when people don't even attend to the issues? Like if you're Sony. Sony has the ugliest engineering interfaces to their beautiful products.
Okay. Yeah, the
let-
products are, yeah, I see. It's a wonderful artifact, but then inside of it, it's a mess.
Well, for example, Walter Mossberg, for you people 50 years from now, 100 years from now, you won't know Walter Mossberg, but he's the personal technology reviewer for the Wall Street Journal. And he wrote a column on Sony's answer to the iPod, which was actually a beautiful little hardware device. It was an elegant device. But he after he goes through and tells you how elegant it is, he says, don't buy this. And the reason is, and then he has these 3 words, Sony's software stinks.
Okay.
And that's the problem, that engineers don't understand what beauty means in an interface.
It's certainly a much underappreciated talent, yeah. You asked me to come back to when I said, Josh, how could he have evolved? And so I better get that off my stack. In other words,
Yeah, okay, so here's the thing I wanted to say. So for the audience, this kind of discussion can get a little tedious and rambling, but this part isn't. This, what I have said what I feel personally, and I've said in public several times, is that there are certain major mysteries, or put it another way, magnificent, superb open questions of the greatest import. And some of the things we study aren't. I mean, if you're studying the structure of databases, that's not one of the big, magnificent questions that I'm talking about. I'm talking about the questions in cosmology, about the Big Bang. I'm talking about the initiation and development of life. But equally mysterious is the arrival or the emergence of intelligence at all. I mean, Stephen Hawking once asked, why does the universe even bother to exist? And you can ask the same question about intelligence. Why does intelligence even bother to exist? the world would go on just as well without us being here, watching it, processing it, understanding it. So why does it exist? And then how did it get to be there? From what did it come? And then how does it work? Now that it does exist and we have wonderful examples, fortunately, we don't have to invent it. We can just, it's all around us. How does it work? Those are the really magnificent questions. And one of them is the evolution of the intellect. And that's when I said, please ask me that again. I wanted to get to this superb, great question. It's why I try to get students to go into AI, because it's or cognitive science. It's a vector into that question. And if they wanted to go into cosmology, I would move them off in that direction too. That's another set of wonderful questions. That's why I go to hear talks by, say, Andre Linda in the physics department at Stanford, because I think those are also great questions.
Good, okay. Now let's see, trying to, well, I guess one of the things it was actually one of the first questions I wanted to ask. I just was waiting for the right moment, but you've accomplished so much over the years. How do you organize your time, every day? How do you, you wake up and you working on one thing at a time? Or do you shut your door sometimes? Are you on the phone all the time? You work in interrupt mode? How do you go through? Or is Monday different from Tuesday?
Yeah.
What kind of scheduling algorithm do you use in your life?
So what I'm doing now in retirement is a lot different than what I did during the major portion of my career, whereas I was a lot more organized about when I did what I did and the concentration I would put into certain things. Right now it's more like a combination of demand-driven and personal interest-driven. Like, damn it, if I'm right in the middle of this Lee Smolin book on the trouble with physics, and I'm right at a great point, I'm going to continue doing that, no matter. Well, if I'm coming down to the Computer History Museum to talk to Don Knuth, I'm going to do that. But otherwise, I'm going to sit there and read that book.
Okay.
Or if I get tired of reading about physics, I'll switch over to the Shakespeare, or whatever. But so it's more like personal attention driven.
So you have a reservoir of a few things that are currently, but you're always working on something.
Yeah, I'm always working on something.
I mean, you don't have too many things on the calendar now as you used to, but you do of course have rehearsals.
Well, the great thing about being retired is not that you work less hard, because what you do is it's kind of interdirected. You always want to. The world has so many things you want to know before you're out of here that you have a lot to do, but it's more like no one else gets to put something on your calendar. That's what I really like. I get to put the things on my calendar.
So, but let's go back then, 20, 30 years. How did you work it then? Was somebody else keeping a calendar for you?
Yeah, always.
And so would you have a leisurely breakfast? You'd come into work and you would say, now what am I supposed to do? And every 5 minutes somebody else comes in the office? Or did you have special days? Did you reserve some blocks of time where you could get certain kinds of work done? I'm just curious.
The honest truth is, now that you're asking me this, I've never really analyzed it deeply. But I would say that there was a, a, some, there were blocks of time allocated to what I would call intelligent delegating. That is, if you wanted to get something done in a laboratory, you wanted to make sure the person understood what needed to be done, and if you weren't quite sure, you would work it out with them, and then they would go away knowing the kind of thing they should do. And that takes time. You can't just, and then you have to get them, you got to get them motivated to do it anyway. So that was part of the time, setting aside blocks of time for that. Another setting aside blocks of time was for intellectual interaction. Like, I just would be more creative when I met with Bruce and Josh together and some of our people. And we were bouncing ideas off the wall, and Josh would come up with 100 different ideas, and 99 of them wouldn't be right, and one of them would be brilliant, and just kind of working that out. So that was blocks of time. And then there was just blocks of time to do. Young people don't understand that life consists of a lot of stuff you just have to do that isn't all that much fun, but you just have to do it. And so you just have to sit down and do stuff like that, like when you're department chairman, or when you're running the computer center, or when you're Air Force chief scientist or something like that. They're just things you have to do.
Yeah, that's, I guess I often sort of schedule the things that, the thing that I most dread to do, but I'll be happiest when I finish, provided I'm ready for it. The hardest thing that I'm ready to do, because in a way, because then I can get stuff out the door, because there's always stuff that isn't so much fun, but if you keep postponing it, it gets worse. On the other hand, if you look at it from the wrong point of view, you say, well, then I'm never having any fun. Because
yeah, I know, that is the big problem. And one more thing I think about the allocation of time is that I tend to allocate far more time than I notice my colleagues allocating to other people. That is, making sure that they, I mean, I really like other people. I really like the people in our department. I really like the administrative personnel in our department. I just want to keep touch with them. And even if there's nothing really to talk about, just go in and say hello and be friendly. And that I just devote more time to that than other people do. So, it's not like I program the time. It's not like I say that tomorrow morning at 9 o'clock I'm going to go in and talk to Peach Turner.
Of course,
it's
right.
just that I just do it. Oh, so Don, I wanted to add a postscript to when we were just talking about getting organized and getting things done. If you look at one level above today's activities, this month's activities, and so on, here's another heuristic for the people watching this thing 50 years from now, or even 5 years from now. You have to have a more global vision of where you're going and what you're doing, so that life doesn't appear to be just Brownian motion, being bumped around from one little thing to another thing. A good example is there's a long chain of activities in my life that stretches from about 1976 to until about 1990, but it makes a coherent, if you know what was going on, this pattern of activities is a coherent plan, very much like the plan that you laid out to all of us back, I don't know, more than 30 years ago, 40 years ago for these volumes. That was a life plan, and it was coherent. You modified it over time, but it was a coherent set of things that gave order to activities. And in my case, 76 was deciding that if AI was going to be, by AI I mean the artificial intelligence part of computer science, if that was going to be a robust discipline, it had to have a robust collection of knowledge. And so I knew that with the set of things I was doing, there's no way I was going to write an encyclopedia of of all of AI. But it needed to be done. It ended up being called the Handbook of Artificial Intelligence, but I needed to get a lot of help from students and research associates and other people who were willing to contribute to it. I guess now, these days, you'd call it a Wikipedia or something like that, but we had a wonderful editor, and from 76 through 83 or 4, we were able to get enough motivation and enough talent together to make a coherent body of knowledge for the field, which tremendously influenced, not at Stanford, but across the board, influenced the development of the field, because people could now buy a book that had it all in it. So that was one thing. Another thing was late 70s, early 80s, capturing the opportunity to transition these ideas from, excuse me, from ivory towers like us at Stanford into companies. That is, getting on board the bandwagon of venture capital people and all those kind of people who want to do this, so that the ideas can get out there as software. So that was a variety of companies to get involved with, including in the mid-1980s getting involved with a big company. I was on the board of Sperry Corporation. Another example of it was same period of time, 83, 82, 83. So AI was known to the rest of the world in terms of a few people who were writing grumbly books about AI, like Joe Weizenbaum's grumble about computer power and human reason, or other people writing about why AI couldn't be done. Well, what about a book about what was being done, and not only what the Americans were doing, but what the Japanese were doing? That was called The Fifth Generation. And it sold a huge number of copies, and you can't imagine how many people have come up to me. I'm talking about dozens, maybe hundreds over the years, saying, oh, I read that book and that's what got me into AI, or that's what got me into computer science. I loved it. I was a double E until I read your book.
May I add that to the list of things that make you happy, is when somebody like that comes to you?
Yeah. And then later on, Peter Hart from, Peter's an old friend from AI. He's been running the RICO laboratory in Palo Alto for quite a while now, RICO Computer Science Lab. He came up by one time in '86 after there were quite a number of successes of expert systems, and he said, "Why don't you just write about the successes?" So I did. We went. Penny and I went out and did a bunch of interviews with people who had done this successfully, and got Pamela McCorduck to help us put this together into a book.
This is expert companies?
Yeah, Rise of the Expert Company is what the book was called. That was a deliberate strategy that gave some shape to what was going on during that period. And to get back to what I was saying at the beginning, make sure you don't get into a random walk situation where everything in the world is demand driven.
Oh, right. Good. Now, actually, you've done very well of anticipating quite a few of my questions that I had to ask you. So that's it means that I wasn't too far off as well, and that we're in the same bandwidth. But I wanted to talk a little bit about Japan. Since the fifth generation and Penny have come up already, and just in, I also remember that when I first came to Stanford, I asked you who would be a good dentist to go to, and you said, "Oh, I've got this Japanese dentist, Mitsu Fukumura," and so we had the same dentist from 1969. That's probably before you met Penny. So I'm just curious as to sort of how your love affair with Japan, and how Japan came into your life and over the years.
They're to the first approximation, there was no thought and no contact, no cognitive or physical travel to Japan before about early 1970s, and besides meeting Penny, who represented for me a link into the big link into the Japanese culture. But aside from that, one of the most startling things that you were talking about me being a gadgeteer before. When I stumbled in on I happened to see the Sony Trinitron television, and I couldn't believe that television could be that good. I mean, it was just a revolutionary way of, it's almost like what people regard high definition now. It's another jump. So that was a kind of a signal to me that something was going on there. In 1972, Jerry Feldman and I went to an IEEE Computer Society joint meeting in Japan, which I think was held biannually. But I wanted to see more about that, and I wanted to make a trip to Japan. So Jerry Feldman and I went around Japan on a tour, and
That was like 3 weeks, or?
72, yeah, something like a 3-week trip. It was broad, but not deep. And but that allowed me to.
What time of year was it? Probably the summer.
I don't remember, but
Long
I
time
don't.
ago.
But it was it must have been some lovely time of year, because there was no physical discomfort of the hot summer. Then then there was some on and off trips to Japan. I don't remember exactly why during the 70s, but in 1979, I had an inquiry from a person, is a mutual friend of me and Penny. Penny knew him through IBM Research when she worked there, and I knew him through computer science channels. Professor Yamada at the University of Tokyo. It was an inquiry about whether I would how about if he nominated me for an exchange award of the Japan Society for the Promotion of Science, and how about if we exchanged houses? So he'd live at my Stanford house, he'd work on campus on sabbatical, and I would be a visiting professor at the University of Tokyo, and that would be, we'd do 1 quarter that way. And so I did that. It was also part of this attempt.
Let's get the timing straight.
79.
You met Penny
72.
in 72, and you got married to 75 or something like that. 70, what?
Yeah.
75. So okay, so you've been married for 4 years, and this will be your first extensive time in Japan then.
Yeah. And so we lived outside, a little bit outside of Tokyo, and I commuted down to the University of Tokyo, and in addition to that, it was part of my job the way this fellowship was set up. It was part of my job to be semi-industrial. That is, I was supposed to go, as a professor, I was supposed to go off and tell industrial people what my ideas were, which I loved. I mean, I loved to talk about expert systems and knowledge-based approaches and so on. So I went around, made a lot of industrial contacts, too, at that time, plus some government contacts through the laboratory, actually a very good laboratory in Tsukuba called, well, it wasn't in Tsukuba at the time, it was in Tokyo at the time, in a rundown old building.
Tsukuba,
Yeah.
the city.
It was Electrotechnical Lab. And
Okay.
then it turned out that, so I made some contacts with them. In fact, I happened to be visiting the Electrotechnical Lab in Tokyo on a day when a typhoon came through. It was the scariest thing. It was the first time, and maybe the only time I've ever been inside a hurricane. And parts of the building were flying off. And
Wow.
but anyway, I made contacts there, and it turned out that group, the ETL group evolved into the group that was responsible for the Japanese fifth generation project.
So
So-
this was in 79.
79, but
It's sort of not quite born yet.
not quite born yet, but
But you were there, and that's why, and then later on you wrote this book about
yeah,
it.
well, so I found out more about it later as it began to evolve. I got an early draft of the plan they were putting together. The plan was very ambitious from an AI point of view. That is what they were trying to do for society using AI that they were going to invent over a 10-year period. But it was very much of a, from a software or theory point of view, it was very much like what McCarthy would love, formal logic, prologue, and from a computational point of view, it matched very much the spirit of the times in parallel computation. It was so half of it was a large investigation in parallel computation. Half of it was using that to do highly parallel prologue on.
Right.
They made a big mistake in that project of not paying enough attention to the application space at the beginning, so they didn't really know what they were aiming at until halfway through. They were flying blind 5 years through the project, and then they tried to catch up and do it all in 5 years and didn't succeed so much. But I wrote a book on it explaining not just their project, but also where the U.S. trajectory had been in thinking about these same issues. And that was basically, like I said before, it was the first time that AI came into public consciousness, and it was the way one of the Xerox PARC people put it in a review that they did of the book. It was Ed telling AI story by using the Japanese in the plot. That's creating a plot around the Japanese to
Okay.
tell AI story, which is not unfair, not
Yeah.
unfair way
Yeah.
of putting it.
Well, you need a plot.
Yeah.
Okay, that's, yeah, it's and Pamela worked with you on that, or book, or was that,
No, Pamela
or was that Penny? Who was the co-author?
McCorduck, Pamela
Yeah.
McCorduck.
Right.
So Pamela McCorduck is at that time and still is Professor Joe Traub's wife. Joe met her in my office at Stanford.
Yeah.
In Polya Hall. Pamela was my secretary then when I was computer center director, and she had been that when I was at Berkeley. She was a undergraduate junior. I don't know if I'd mentioned this in my past interview, but she was an undergraduate junior, and she was the first secretary that not Jerry Feldman, but Julian Feldman and I at Berkeley had
I see.
on our project. And so Pamela and I were on each other's wavelength for a long time, and by that time she was by 82 she was quite a mature writer, had published several novels, and
Yeah, I've got a couple of her the novels that she wrote.
so
that-
what I did was talk it through with her. It's part of this discipline problem you were talking about before. Just getting it done by working with other people, collaborating, rather than just sitting down and doing it as a loner. And Pamela and I would sit for hours and talk about this. And
So do you still visit Japan frequently?
yeah, I visit Japan now 2 times a year. In fact, I'm going to be going on May 20th. This is, for those people 50 years out from now, this is 2007. I'm consulting for the Air Force Office of Scientific Research that has an office in Asia, headquartered in Tokyo, to sponsor research in Asia. And I'm their consultant on computer science and AI research. So I do 2 weeks, 2 times a year. And we used to do it a little more often when Penny's mother was still alive. We'd go back there.
That was
spend
her,
some time with
that, she doesn't have other family
Her
particular?
sister and
Yeah.
her younger brother live in Tokyo.
Okay. Good. Okay. Now, let's see. I got couple of important ones I might as well.
Don, I want to
let's-
back
yeah.
up just a second.
Yep.
I want to say two things about the Japanese and my interest in them. One is a tremendous admiration for their skill, intelligence, and diligence. It's just really superb. The other thing, even bigger, is my feeling about this is a very fuzzy thing to say, but I don't mind being fuzzy. The Japanese aesthetic. You can just pick it out anytime you see it, and if it's not there, you know it, and if it's there, you love it. It's for me. And the Japanese aesthetic is just wonderful. And so it's a, excuse me, it's a pleasure to browse through Japanese literature, to look at Japanese designs, to visit things in Japan. It's not that all of Japan is that way. Some of it is just a big bloody mess. But
Well, you were talking about the new iPod competitor, for example.
yeah,
It had elegance in some parts of it and not in others.
That's right.
And it's really hard to. I mean, these are really orthogonal types of expertise. But I know what you mean. There's and that's what drives a lot of our work too. In science, we have the same aspects of taste and stuff. Now, and you can't expect everybody to have it all. That's why the world is so interesting, because we get lessons from all the different cultures, and we can celebrate that. I wanted to talk a little bit about a phase that we haven't said much about, and that is the work that you did in the 80s about the blackboard model and in connection with computer design.
Yeah.
Just so some reminiscences about that aspect, and how does that fit in with, well, maybe the fifth generation, if at all, or with the other things we've been talking about.
I'm going to start back with what AI people call the blackboard model. Those of you out there are going to have to go look it up, because there's no time to tell the story here in detail, a technical story, but you can find the story in a 1990 book, roughly speaking, 1990, by Robert Engelmore, called Blackboard Systems. It's a collection. Blackboard Systems. AI people have a variety of underlying problem-solving frameworks that they use. They combine a lot of knowledge about the domain, typically, with one of these underlying frameworks. And these frameworks can either be kind of forward-chaining kind of framework, or sometimes called generate and test. Or they could be backward-chaining frameworks, like here's the theorem I want to prove, and here's how I have to break it down into pieces in order to prove it. I was doing a, excuse me, at DARPA's request, again, for those people way out there in the future, DARPA is a U.S. Defense Department research agency that was funding a large portion of computer science research throughout the 60s, 70s, and even up to today. But they asked me to take a look at a military problem, a defense problem, not a problem of attack, but a problem of defense, which had to do with defending against quiet submarines in the ocean, basically finding those submarines. Where were they? And the problem was that the enemy submarines, in those days, the enemy was the Soviet Union. Soviet submarines, they're pretty good engineers, and they were in the Soviet Union, and they were designed their submarines to be very, very quiet, and so did we. But the ocean turns out to be a very noisy place. So the signal-to-noise ratio out there in the ocean, listening with hydrophones to the ocean, was very hard to interpret in terms of where the submarine is. If there was a submarine, where is it? What's it doing? So I didn't think I could solve this problem, but you can't say no to DARPA. So we headed into it. Penny, my wife, was the chief engineer of the project. It was not at Stanford because it was classified. It was right off campus in a little contract firm off campus. And I tried the same hypothesis formation framework that had worked for Dendral, and it didn't even come close to working on this problem. So fortunately, the Carnegie Mellon people, Raj Reddy and Victor Lesser and Frederick Hazeroth, had come up with another framework which they were using for understanding speech. It was the DARPA National Speech Understanding Project called the Blackboard Framework. It never worked for them, but I picked it up and adapted it for our project, and it worked just absolutely brilliantly. And it allowed an arbitrary combination of top-down reasoning and bottom-up reasoning from data to be merged at different levels, which, to use terminology we were earlier talking about, are really levels of abstraction in the problem. And there would be experts in the world who were experts on how to go from this level to that level, but didn't know anything about the other levels. So this is a world composed of a lot of experts. In the program, we called them knowledge sources. And the knowledge sources, each knowledge source would have a kind of a human name for their body of expertise, like there were people in the speech world who knew about phonemes, and there were other people who knew about pragmatics, and there were other people who knew about semantics, and there were lexicographers and grammarians, and these were all individual experts. But what we did was put together, we're using this so-called Blackboard framework, a collaboration framework where they could all collaborate on a common solution, which was being built on, of all things, a place called the Blackboard, which was a commonly available data structure, with all the reasons why each knowledge source gave for its evidence for why something was valid at a certain level of abstraction.
Is it similar to what people use on video conferences now, where they have the software that people are adding to, I guess it's a whiteboard now, but they have, but it's sort of a display that everybody, all participants are viewing,
well,
and erasing on.
That's correct. And the difference there would be in what you're talking about, it's all people, not programs. Mm-hmm. We nailed it down a little less fuzzy than, we were a little bit more structured and analytic than you would find in these video mm-hmm. conferences. Mm-hmm. But it was a similar idea. Mm-hmm. We actually produced a program that in its test version, prototype version, no, I'm sorry, scratch that. Its prototype version was so promising that DARPA continued it for another 2 years, and they made the prototype version into a solidly running version that was tested by MITRE Corporation tested against the behavior of humans doing the same thing on the coastal stations of the West Coast. And the program did better than people. Doesn't mean anything to the Navy. The Navy just couldn't cope with it, and they never installed it, but it did the job. So then we used it, but it was classified. So what can you rescue from a military classified situation? Well, the only thing the government cared about was the classification of the frequencies of noises being made on Soviet submarines. They didn't care about the Blackboard framework. That was computer science. So we rescued that in 2 ways. One was some papers that were written in AI magazine. Penny wrote 2 really much referenced papers. And we did a kind of hypothetical how to find pandas in eucalyptus trees. Very, very difficult to find a panda in a eucalyptus tree.
I see, not a submarine.
What?
Okay.
And the other thing was we did another, we started another big application, which was in the non-classified area, which
Isn't it
was...
supposed to be koala bears? I'm just,
Oh, I'm sorry, not pandas, koala bears. You're right, koala bears and eucalyptus trees, not pandas. Right, how to find a koala in a eucalyptus tree, which arose in a trip I took in Australia, and the forest ranger was trying to point out the koala to me, and I couldn't see the koala. It was just like a Soviet submarine in the ocean. Well, then we did a very complicated application, which was one that hadn't been done before. It had been done with massive amounts of computation, but the world didn't have that much computation, and you needed a kind of heuristic method for doing it, knowledge-based method, and that was X-ray crystallography, interpreting the electron density of crystallized proteins in terms of what atoms were attached to what atoms in what geometric structure in this crystal. And you needed not only knowledge about the physics of electron density, which was one blackboard plane, but we also had a chemistry blackboard plane because you needed knowledge of chemistry as well as that. So it was the first time that there were what we called intersecting blackboard planes. And it was also another very successful application. So then now we're, time-wise, we're up in the late 70s, early 80s. And now the zeitgeist was calling for working on parallel computing. There were, Gordon Bell had started a company in parallel, with parallel processors. And I had talked to Gordon quite a lot about how to structure them. There was another one that Ben Wegbright was heading out here in Silicon Valley, which combined with a third one, I think, to make a company called Stardent. Anyway, there was quite a movement toward, on thinking machines.
are you talking about general purpose parallel machines?
Yeah,
or-
general purpose parallel machines.
Like
So-
Gordon Bauer and
Huh?
I mean, okay, but the psychologists are
No, Gordon Bell.
Gordon Bell, excuse me,
Yeah.
okay.
Not Gordon Bauer.
Yeah,
Gordon Bell had left DEC and
yeah.
was started.
Oh, yes, of course, and he went to NSF at about this time, wasn't he?
Yeah, he did at some point,
Yeah.
but then he started a company
And promoting parallel.
in parallel
Okay,
machines.
right, okay.
So when I looked at that, I said, maybe we can, to do AI problems, the Blackboard framework was ideal because the activities of the different segments of computation could be not totally, but largely parallelized by these different knowledge sources working on different pieces of the problem, either communicating to a common blackboard or distributing the blackboard to all processors all the time, an updated blackboard. And so we started down that track. DARPA liked that idea. We borrowed a computer designer from DEC, Bruce DeLoggy, and we had Harold Brown, one of our really good people, a mathematician working on the problems too, and some graduate students. And we worked on the problem we were simulating parallel machines. The reason being that I had no interest in building anything. In fact, I didn't even believe in building anything. I believe you ought to test out the ideas before you build it. Building is expensive, and if you got the wrong thing at the end, you'd be very unhappy. Mm-hmm. Well, it turns out that in that particular game, namely the game of architecture of machines, if you're a digital systems lab, what do we call them? CSL persons, computer systems lab person in our department or similar departments, you don't have any credibility at all if you do it at the software level. If it's not at the hardware level, it doesn't exist. So it was almost impossible to communicate ideas to these people. First of all, they weren't interested in AI things anyway. Second of all, it turned out that there was, with Moore's law operating, there was plenty of power anyway for the AI methods to work on ordinary machines. You didn't really need parallel machines. So it was an extremely interesting endeavor, but it didn't really come to anything then. But now we're running out of gas on Moore's law. And now you're finding Intel and AMD are putting, it used to be 2 cores on a chip, now it's 4, it's going to be 8, they're talking about 16. That was exactly the range of multiprocessor activity that we were doing then. We weren't doing thinking machines type stuff with 1,000 or 10,000 processors, each doing little things. We were using a few processors doing big things, knowledge sources for a blackboard. And so I'm getting the feeling that we have to resurrect some of those papers, like doing a volume of selected papers from that era to resurrect those ideas. Long story.
Right, no, that's another case where something happens before its time, it doesn't mean that it has to die, forever. And very few of the things that have ever been discovered about computers turn out to be never useful. They're always dominated by something else. Once small change in hardware capability can mean that all of a sudden something is much better than the other thing, which used to seem to be better. Right. Now let's see. I guess I should ask something about the experiences of starting up companies, because that's a big thing, although that's not one of my personal interests. I'm doing it only because I know there are people watching who are more interested in the I mean, it's important for the world to people to make a living and all that, and so I have to admit my own bias is less in that direction, but still, that's my own problem. I know that there's Intelligenetics, the Technology, IntelliCorp, or was it different? Maybe more companies, and you mentioned Sperry Rand, that where you serve on the board, but I'm more interested in the startups. I think some of the stories associated with that, and how you got the idea to do it, to come during the night or whatever.
Okay. Good. So that also is a package of stories. Let me start by saying that that there were really 2 inspirations for starting companies. One was kind of a general inspiration, and the other was quite specific. The general inspiration was wanting to get your ideas out there, and along the way, making some money on these companies, just like some of us do consulting, and it was that sort of thing.
I understand.
And not only for yourself, but also involving a lot of the people in your
you see that the world, nobody's rising to the occasion, and the world needs something. And I had the similar thing, with fonts and so on. I didn't mean to.
No. So let me head down the story. So then the specific inspiration was that there's a Stanford culture that it's an order of magnitude stronger today than it was at that time, but at that time it was still very strong, in 1979. It sort of comes out of the Hewlett-Packard life story of people starting companies. It was Varian, the Varian brothers, being professors at Stanford, started Varian, and Hewlett and Packard earlier than that, and there were several stories, even smaller stories. Elliot Leventhal starting Leventhal Medical Electronics, and maybe a dozen other companies. But right about 79, there were a group of companies that were being born in connection with the emerging biotechnology out of the medical school. In fact, so many companies were being born that Don Kennedy, who was president at the time, started to worry about whether he had to have special regulations at Stanford to regulate conflict of interest between faculty and the companies. That's how many companies there were. So
when did Geraci?
Geraci's work was never part of... Geraci came here to Stanford as a joint that is a 50% appointment in chemistry, 50% doing his company, which was Syntax.
Already, yeah.
And
Right.
it was early on that Stanford and Jurassic got together on the great idea to put Syntax in the industrial park, rather than in Mexico City or wherever it had been born. Okay, so in that atmosphere, in that environment, we saw two things unfolding. One was that there was a very large demand for a piece of software we had produced in the Heuristic programming project, which was the software generalization of the Myson medical diagnosis expert system, called eMyson. Very large demand for that, and a smaller but substantial demand for a blackboard framework piece of software that we had developed called AGE, A-G-E, which modestly stood for Attempt to Generalize. We were attempting to generalize what we had done in the sonar and in the crystallography examples. So that was one example. That was one instance where there was a lot of what you might call user demand for this stuff. Companies were after us. We were shipping out literally hundreds of copies of this software and documentation. It seemed like a company could do that better than a laboratory. The second place where we had a lot of demand was users coming in over the ARPA net. Maybe by that time they were coming in on the NSF net portion of the network, but they were coming in to use the SUMEX machine to do sequence manipulation in the unfolding, emerging sequence databases that were being built at the time. It looked like that was also the basis for another company, because a company could do that. I mean, why should we waste our PDP-10 resources serving the nation for this when they could be buying it from a company could run it and they could buy it from that company. And
was it university researchers, or were these other companies buying the time?
A combination of both. Combination of both.
And when you say at the time, I mean, are these companies? I'd like to sort of put dates on them.
So dates would be.
So which were first? What was first, second, third, and approximately when? You know, or did they all start out at the same time? Or
Yeah. Okay. Great. I'm going to put dates on them.
Yeah.
So I'll have to edit this when the transcript comes out and get the exact dates. But in 1980, we decided to move forward. Well, we were in conversation about moving forward on both fronts, the biology front and the expert system software front, in two separate companies in 1980. It was easier to get the biology one moving first because the only people involved were myself, the two biologists, and Peter Friedland. We got another person involved, a graduate student in the Graduate School of Business who was taking a course on how to write business plans. And so we got the faculty member to target him at us, and he wrote our business plan, and we sold it to a venture capitalist who I happen to know because they were friends of Ed Fredkin. We were talking about Fredkin before. Friends of Ed Fredkin, and Fredkin had gotten money from them to start a. You remember PERC, the computer company?
Yeah. I invested.
Yeah, I invested in PERC, and so did Raj, and so did Herb Simon, and you now. And anyway, Fredkin knew these people, and therefore I got to know them. And we got Intelligenetics up and running in roughly speaking, late 1980, selling sequence analysis software on a DEC machine that was networked in some way, and I'm not sure how. Maybe it was via the timeshare net or something else at that time. The other company was called Technology, and as you can see the difference in the names, Intelligenetics points to biology,
right,
and tech knowledge points to technology and knowledge-based systems. And there it was not 4 people or 2 people, it was 20 people. Because my view of that was that everyone who had helped us get to this point needed to be, in some sense, rewarded by being a participant in this new enterprise. So I just made a list of all the people who helped us, who contributed something, like the graduate student who did EMICEN, and Tom Rinfleisch who helped us with SUMEX, and Bruce Buchanan who was, at that point,
Philosophy.
so like associate director of the laboratory, and Bob Engelmore, and for Blackboard Systems, and Penny, and my wife, and people like that who had contributed. Plus I got in 2 other people. One not from Stanford. One, Randy Davis from MIT, who had contributed a little bit earlier, but had left. And the other was a very good articulator of the ideas from Rand Corporation, a guy by the name of Frederick Hayes Roth.
Yeah, and Denny Brown was involved with that, with technology too?
Denny?
Denny, yeah, or no? Okay.
I don't think so. I don't think he was. I'm not sure of that, but I don't think he was, because I don't think he was a member of the Knowledge Systems Lab, of the Heuristic Programming Project, which later turned into the Knowledge Systems Lab. Now, starting a company with 20 people it's bizarre, and I didn't know it at the time. It's only later when people in the entrepreneurial world who know about these things basically said, "Are you crazy? You can't do that. You have to have a group of people who think in common, act fast. That's the way the culture works." But I never thought that 20 people would be a hard thing to do. Turned out it's like herding cats.
Oh,
okay. And it was a lot more difficult than we thought.
It's also a big responsibility.
It was.
I mean, you're affecting their lives so, so directly. It's not just like being a teacher.
Well, I had thought that we would get a professional businessman to run the thing. The professional businessman would get venture capital, and then using the venture capital, they would hire good people. Instead, what happened was a significant chunk of our own people gravitated over there because the work was exciting, it was a new thing, and it was paying a lot more than we were paying. So in a way, we kind of decimated our laboratory by doing this. Anyway, long and short story is they spent a lot of money. They being the professional businessman that we hired, tried to negotiate a intellectual property agreement with Stanford for the rights to use the EMICEN software that had been developed at Stanford. Stanford at the time they were very much of a novice in the area of dealing with small companies. They still are difficult, I hear, but they were impossible at that time. So the guy just said, okay, technology will develop its own, forget EMICEN. And they spent a lot of money doing that, and by the time they finished doing that, Osborne had a $1,000 version of that software out, or maybe a $100 version of that software out and running on the early PCs, and their $5,000 version wasn't going to sell. And so it didn't work out so well for that company, and then eventually it got sold. It's still, and then it resurrected itself. It's still in business, it's still in Palo Alto, it still employs a couple dozen people doing military applications mostly. Intelligenetics couldn't get a grip on the biology software market because those people at the University of Wisconsin I was telling you about before basically were offering the same thing for free, and PCs were coming into play. So you didn't need 1/10 of a PDP-10. You could buy your own PC for $2,000 and run the University of Wisconsin software for nothing. And
I see.
so So it changed its name from Intelligenetics to IntelliCorp, and started to sell a version of some software it had licensed from Stanford that we had done in our laboratory, which was one of the first languages that incorporated object-oriented programming with inference methods. It was called KEY, Knowledge Engineering Environment, developed by Peter Friedland and Mark Stefik and a few other people in our lab.
Did this run on PCs or a workstation? I mean, in
Ran
those
on-
days, there was quite a difference between a personal computer and a workstation.
Intelligenetics was close, this was before it became IntelliCorp. As Intelligenetics, it was close to being Sun's first customer. I don't know if it was Sun's first customer, but
Okay.
because I knew of the emergence of the Sun workstation at
Yeah.
Stanford, and I knew what power you could have for a few $1,000 in that workstation,
Yeah.
I immediately oriented the company, the business guys, to go make a deal. And that was when Vinod Khosla was president of Sun, not,
Oh,
it was the very earliest president.
yeah.
And Sun was still stumbling around. In fact, they weren't really such a good vendor because their machines weren't that reliable at that time. But we were a very early customer. And then IntelliCorp I think they pursued the same strategies to offer it on workstations, but by that time the Lisp machines were out. And this stuff ran really well on Lisp machines. So they were selling them on Lisp machines. They were selling them on the Sperry version of the Lisp machine, the TI version of the Lisp machine. They were selling them on the portable versions of the Lisp machine, the desktop versions of the Lisp machine, whatever they were called, micro something or other. And they had lots and lots of applications, the very sophisticated applications that they were doing. They too never got business traction and lasted right through the dot-com bust until, during the dot-com bust they went bust. So they lasted roughly speaking 20 years. Intelligenetics and Intelligenetics got spun off and was sold to Standard Oil Research who wanted to get into molecular biology applications. IntelliCorp lasted about 20 years. Technology is still in existence. They're all in the space called the living dead, where they're not big like Google or Yahoo or eBay, and they don't go out of business right away. They just provide enough business to keep their employees employed. There are lots of them lots of these companies in Silicon Valley. Then there was a third company, which I started jointly with a professor in the civil engineering department at Stanford, doing, so one of IntelliCorp's...
Who was that?
I'll put it into the transcript.
Okay.
Ray Levitt.
Because I was thinking the civil engineering have some kind of a blackboard model that they use for scheduling job. I mean, you know, the electricians put up their data and you know, and the other contractors too.
Yeah, that could be that could be the case because one of our PhD students ended up running their big laboratory over there, John Kuntz. And so that could be, I just don't know that. But,
excuse me for interrupting.
But anyway, one of the customers of IntelliCorp in Europe, in Finland, was using Key to do engineering design of gigantic boiler systems for huge factories. It was one of the earliest applications of, maybe the earliest application of AI to engineering design. And it looked like it should be just a really great AI application area where you could sell it for a lot of money into companies that would save a lot of money using this software. And it was in Lisp, and it was programmed in Key, which ran in Lisp, ran on workstations. We started a company called...
When you say Key, I'm not familiar with that. You spell it?
Key is Knowledge Engineering Environment, KEE.
KEE, okay.
It was an object-oriented system on top of Lisp that also incorporated inference software in its methods.
KEE, okay.
KEE. It was actually designed, believe it or not, it was based on some software at Stanford, but redesigned by Richard Fikes, who was vice president for research of IntelliCorp.
Okay.
So it's one of Richard's great contributions, was Key. That company, Design Power Incorporated, was the two Finnish guys who had developed the software came to the United States, and with permission from their company, I don't know exactly, I can't remember the grounds for using the intellectual property from their company, but they plus one person from Silicon Valley kind of launched this company. I was one of the founders. Ray Levitt was one of the founders. And it had a very difficult time selling into the sales that we thought would be so obvious just weren't. The companies were, there was a tremendous amount of inertia in the big engineering companies to adopt this. Eventually, so the company kind of went partially bankrupt after its first round of venture capital. It couldn't get another round of venture capital because there was some difficulty with Finnish investors that were in this company. They didn't quite understand the ground rules of Silicon Valley, and they basically screwed up. And so the original company had to reconstitute itself. But in the end, they did survive long enough to be bought by another software company about a month ago, in 2007. So in the end, their ideas still survive, and the software still survives, but not in a big way.
Okay. Well, now,
Oh, one other thing,
yeah.
Don. I just want to mention that during the dot-com boom, I was approached by several people who wanted to use expert systems in their, whatever their categories were, that they were trying to exploit web-based something or other.
Right.
And would I be a helper, a guru, an early investor, et cetera? And I did some of those, and some of them turned out to be extremely good. Like one of them merged with a company which merged with another company which is now shopping.com, and it was expert systems for the shopper.
Okay. Well, that's good segue, unless you have something else you want to say about company. I mean, I wanted to focus on expert systems, I mean, as it relates to, interacts with other streams of AI. And these are, I know that Nils is going to be interviewing you about this, but I wanted to bring it out
Sure.
too. So, I mean, artificial intelligence is a huge subject, and it doesn't only have neats and scruffies. I mean, it also, so I'm thinking, for example, of the strains, like Stuart Russell, Berkeley and Daphne work, and I was looking at there were a couple of journals in the library. There's one journal called Heuristics, and another one called Heuristic Methods or something, Heuristics. I don't know. There are two journals that start out with heuristics in the title, and so I was browsing through them the other day as I was in the stacks, and but I looked in the issues from 2 years ago or something, and it would say, no, I'm sorry. There's a journal called Expert Systems.
Yeah.
Right. Expert Systems and Expert Systems with Applications,
Yes.
or something like that.
Right.
That's what I'm thinking, not heuristic. But I looked inside, and one, a certain percentage of the papers were about expert systems, but others were about fuzzy logic, or genetic algorithms. So maybe this is all, all of a piece, but there's all these many currents going on. There's neural nets articles in there. I know the Japanese use fuzzy logic for everything. I don't know why, because I never understood it. But so we've got Stuart Russell's approaches to what we call it automatic learning. For machine learning, and they're Daphne, Bayesian nets. There's fuzzy systems. There's Doug Lennett's gathering of knowledge bases and all these things. So, can you, in 25 words or less, or just to
Try to sort it all out.
How do you how do you view this map?
Right. Very, very, very good question. it really won't, I'm going to do it, but it won't be 25 words or less. It might be 250 words or less.
No, I don't want it to be that small, short, but
But anyway.
I'd like a guide
Okay.
to the perplexed.
So,
Yeah.
so once upon a time, there was, to use words I just got right out of Lee Smollen's book on physics, there used to be exact knowledge in our expert systems. That is, when we first started, we started with atoms, carbon atoms, oxygen atoms, valences, chemical graphs connecting these things, rules for breaking bonds. Either the bond broke or it didn't break, and there was and these were if-then rules for representing this knowledge. And we had a lot of that knowledge, and none of it was fuzzy. None of it was probabilistic.
Probabilistic.
Or in any way probabilistic. Then
Mice in it had to become.
then we came in, we stumbled into, so Ted Shortlift started working on Mycin, and then it turned out that doctors wanted to represent their knowledge with a little bit of fuzziness. In fact, they were using several English language words that covered the space, like likely, or unlikely, or a couple other variants of that in the middle. I forget the details, but there were common words in medicine. But there were only like five of those. And Ted expanded that to be 10 categories, not 5. He could have probably gotten away with 5, but he did 10, and set up a little ad hoc calculus to combine those numbers into what he called a confidence factor. Do a little bit of reasoning in the background with this confidence factor. Now, that kind of ad hocery, we used it incidentally on the sonar thing, perfect. It was just wonderful. It just worked perfectly.
Sonar?
Remember that sonar example of finding submarines in the ocean?
Oh, yeah.
We used that.
The classified.
Penny and I just used
Okay.
short-lived scheme right out of the box, and it was great. Let me tell you the next step and then go back a step. The next step was, that got a lot of people unhappy. If you're dealing with something where the words were likely or unlikely or that, my God, we mathematicians have invented a whole calculus for that. And why are you being ad hoc about it? Why all this ad hocery when you could use mathematics? Frankly, that was almost exactly the kind of words that you would hear. And to which the answer was, hey folks, you don't bring a big cannon to bear on something where you don't need it, where a little pop gun would do. So let me go back now and give you an example from Jurassic. And here's one of the world's great minds, one of the world's great mass spectrometrists. We're showing him, we're extracting knowledge from Carl about some mass spectrum. Mass spectrum has molecular fragment weights along the x-axis, and it has relative abundance of fragments at that weight on the y-axis. And we were setting up rules for the fragmentation of certain molecules that were showing itself that way, representing itself that way. And we said, well, Carl, what are you going to do with these y-axis points? He said, well, first of all, let's ignore them. In other words, it was 0, 1. Either the fragment was there or it's not.
Okay.
And we said, wait a second, these are lots of peaks. You're not going to ignore the heights of the peaks, are you really? He said, okay, I'll tell you what. We'll just call them high, medium, and low.
Okay.
So all that the chemists needed was either it's there or it's not there, or else the most they wanted to use was high, medium, and 3 values. So we went to go back to the thing we were saying, well, you don't really need, you can set up a very simple logic, an ad hoc logic to deal with this. Along comes Latvisada and he says, I'll put in some systematic logic into that. It wasn't exactly what the Bayesian logic that's being used now. It was more like a Latvisada. It was less ad hoc than ours, but it was still pretty ad hoc. The Japanese got to love that. They got to love the idea that there was a little calculus involved, a little mathematical calculation involved in doing that. So the first application that was done in Japan was, I helped to advise them. It was done in Hitachi System Development Lab, and it was to control, an expert system to control the braking of subway trains in Sendai. And you didn't want the subway train to come to a sharp stop, which would jerk all the passengers, and there was expertise in the conductor, and the conductor would use his expertise to know how to apply the brakes. Well, he needed a little bit of fuzziness there to accommodate certain situations. So it got generalized, I mean not generalized, but it got used all over the place, from subways all the way down to fuzzy rice cookers. But these were little expert systems with 20 rules, 50 rules, but with a little ad hoc, almost ad hoc calculus. Well, then came a couple students of ours, David Heckerman, Eric Horvitz. Remember them? David won the ACM Thesis Award the year that his thesis was done. Both of them work at Microsoft Research now. And they were working with Ron Howard in the Industrial Engineering Department on a more systematic decision, what shall I call it, decision-making algorithm structure. And that turned into what are called belief nets and these Bayesian analyses. So then it became really sort of a hot topic. Then you didn't have 5 people working on it. Then all of a sudden, you had 500 people, or 50 people at least in the field, working on those kind of issues. And that became its own little field. And any field like that becomes self-propagating. And it doesn't matter if Ed Feigenbaum keeps standing up and saying, you guys don't need that armada. There is no reason for coming out with a number like 0.69108. It doesn't make any sense at all. And these problem-solving activities are more or less qualitative.
Yes.
In the way polio would have thought about it. It doesn't. That has no effect on people. It's what I call physics envy before. They absolutely have to have it. Okay. I look back at the paper that Wigner wrote, which was the paper in 1961 or 2 on the unreasonable application of mathematics to the physical sciences.
Unreasonable effectiveness.
Huh?
Unreasonable effectiveness.
Yeah, effectiveness. And say, well, just, even for physics it was unreasonable. Why do you need it for this stuff? And yet that doesn't have any impact. And so when you read Stuart Russell's book with Norvig, for example, on what he calls artificial intelligence, a modern introduction, what he means by modern is, I'm going to get rid of all that scruffy stuff and I'm going to put all the neat stuff in. Okay. And then you get Nils saying, like he did at the AI Lab retreat 2 weeks ago, he was saying, I used to be one of the neats, and I wrote a book with Genesaris on it, and now I'm moving in the other direction. I'm a scruffy now.
Well, I don't think you have to be either or, do you? I mean, can't you appreciate some of the talents of
I think so. And I think that's the way it's going to end up, is that, right.
Of course, I work with font design, and it's a similar thing where if you look at the people who are getting drawings from a great designer, they will measure everything with a micrometer to see exactly where his ink stroke went. But if you have the designer in your office with you, when Herman Saab came to visit me, oh, this looks like about 1 to 4, let's, and you just do, these decimal points was not
the question is, why burn up a lot of graduate student time and faculty members' time and pages in the journal?
No, but I think the fuzzy logic people would say, well, but we really aren't concerned about the numbers so much as the axioms that these things satisfy, and then they can then get a higher level view of it once they know that there are some algebraic operations that they can do, and then they can use that as a guide to taking the next step. So that's why I'm saying we don't really necessarily have to. I mean, some people might might, wear their neat hat one day and the scruffy hat. So sometimes they might be both in the same body.
Yeah. Let me tell you one more thing. The Doug Lennet work doesn't fit into this paradigm at all. Doug's work is orthogonal. Doug's work is whether or not you use any numbers at all to characterize these relationships, Doug's work is to prove that huge amounts of knowledge will explain or will replicate common sense reasoning, and that there is nothing to common sense reasoning but a huge amount of knowledge.
Okay.
And huge for him, right now it's 5 million things, and maybe it needs to be 500 million things.
How does common sense affect versus experts? I mean, experts is uncommon sense?
Yeah, exactly. An expert, so Herb Simon did a series of studies after he said he was influenced by the expert system work to go look at what it takes, what makes a human expert at something. Mm-hmm. And his paper with Bill Chase, for at least in the case of chess playing masters, indicated that the chess masters knew about 70,000 things, plus or minus 20,000 things, of specific chess lore, more than the amateurs knew. And that it takes about 10 years to acquire these 70,000 things. And so that's not the 7 million or 70 million or 700 million things that Doug is after. Mm-hmm. It's a narrow thing. Mm-hmm. I don't know if I told you that story about the pulmonary function diagnostic guy. We worked with a guy, when E. Meissen was born, Penny and I decided we are going to test out whether it's indeed the case that you could shove a new domain into E. Meissen quickly. So I had a relationship going with Pacific Medical Center up in San Francisco, and I knew a guy up there who was a pulmonary physiologist who did lung disease diagnosis from a machine called a spirometer. It's a machine that you breathe in and out of. I don't know if you've ever used it. You go, and then the curves of your breathing show up in your intake and your outflow of air. And from that, they diagnose the condition of your breathing apparatus. And we worked with him for 3 weeks from the first 100 cases that he showed us from his files, got a good set of rules, polished them with test cases from another 100 cases that he had. By the end of 200 cases, we were at the point of diminishing returns. We had it. We nailed it. And we nailed it with 400 rules. And this guy looked at and he said, "Is that all it is? Is that what I know? 400 things?" And we said, "Yeah, Bob, it looks like it." And he gave up doing that for 5 years. He went and did something else. Because he couldn't stand the idea that what he was doing was captured by 500, 400 rules. Well, it might be 70,000, but common sense is way, way more than that. Common sense means almost everything you know.
I see. Okay. And what about I'm thinking about Rod Brooks. The physical-based intelligent, or whatever,
Yeah.
the way things they just are little motors that are interacting by evolution in ways that aren't understandable by logic.
Yeah. So it turns out Rod himself doesn't believe that anymore. But it's not because he changed his mind so much, it's just that it was obvious that what he was proposing wasn't the whole story, and he's just come to encompass more of the whole story. It's called it's the view that the world is its own best representation. So don't try to represent the world.
Embodied or something is one of the buzzwords that I heard at MIT.
I don't know that.
Okay.
I'm not sure about that buzzword, but
Yeah.
but the idea is don't try to capture the details of the world like McCarthy would do in formulae, but instead just respond to the details of the world in whatever is a useful way to respond to it. So if you're an insect and it's a pebble, responding to it might be to lift up your leg, to touch the pebble and then move on. Well, all of us, so my interest in AI is conceptual reasoning. So in fact, my goal, I kind of called it when I wrote the article for JACM a few years ago, 2002, I think, trying to redefine Turing's test. I call this goal Einstein in a box, and I really meant it. I really meant that I wanted to replicate the mental qualities of an Einstein in terms of conceptual understanding, reasoning, deep reasoning, insightful reasoning. And I said to Rod, what you're doing is great for insects. You know, you might make the world's best insect, but so what? So it's the world's best insect. Now, that's not really fair, because years before, eminent psychologists thought exactly the way Rod was thinking. Like Skinner's stimulus response is exactly the way Rod would describe what his leg on his robot was doing. It felt this pebble, and it responded by lifting up the leg. And Skinner, you know, was famous. He won all kinds of awards for believing that you could frame human thinking that way. And his view was there's like a big fight between Skinner and others. I can't remember the name of the psychologist, but he was responsible for a brand of psychology called mental maps. And there was a big fight in the 1930s between Skinner and the mental maps people, and the mental maps people won. That is, we do have a representation of the world in our head. It is a symbolic representation. Mice have it, not just humans. So, but you can't blame Rod. I mean, that's a viewpoint which has a distinguished background.
It still might contribute to common sense.
You mean stimulus response?
Yeah.
Yeah, sure. You see something and you just fire off on it. Yeah.
Right. Now, okay, oops, we got 5 minutes. I want to, if necessary, we can go to another tape, but I think a nice way to sort of, let's look now vectors to the future, and if you have some last words of advice to people, you know, that, I hate if somebody asks me to predict what the future is going to be, but if you, so I'm giving you a choice of 2 questions here, either to say what you think is going to happen after today, or you can also say, you know, besides everything else I've been mentioning, what do I want to tell you, people of the year 2050? So.
Yeah. Let me address let me say the answer to your question at 2 levels. The level of the person who might be watching this, a young person, maybe undergraduate or even a graduate student who has a full career ahead of her or him, and then the person who's watching this thing out 50 or 100 years from now. To the person watching it, to the younger person who's looking for career tracks, I would predict, I would advise, actually, which is another way of saying I would predict that it's a good thing to do, to first of all, to work on the modeling of, we're making good progress again after a while, after an interval, on the modeling of human cognitive processes, and that is a really serious goal. It's a goal of AI that it comes and goes. AI was largely engineering for a long time. It started out as largely psychological modeling. There's now a lot of data coming in from neuropsychological modeling, neuropsychological data gathering, that right now is not of immediate benefit to the modeling, but it's going to be. And it's a good time to be getting into that field to try to figure out more of how a brain functions. Now, I'm not talking about how the physical brain functions as much as I am talking about how the mind operates in this machine called the brain. So more work on that area. This is a good time to do it. Another good thing that I predict will be coming along is in the artificial intelligence, the engineering part of our field, not the modeling of cognition part of our field, the use of AI programs to find complex relationships in the immense databases that are being collected right now. Another way to say that is, it goes back to that original goal of Lederberg's and mine to do science by machine. I talked to a researcher at UC Davis last weekend at the National Academy who was working on a gigantic data collection experiment in astronomy, astrophysics. With his sensors were just pulling in like 50 terabytes a minute or something like that. He just huge. And he was saying, what I really need alongside of all of this is, he was asking me if I could supply it. He says, I need a good guessing machine because I can't look at all of that data. I need something else to look at that data and basically come up with good what Polya would have called the art of good guessing. We would call clever hypothesis formation. There's going to be a lot of that. We're not going to get the Einstein in a box, but we'll get a lot closer to the Einstein in a box in the next decade or two, and that's a very good problem to work on. Now, notice that I'm talking about structural, conceptual relationships among concepts in the data. I'm not talking about superficial relationships such as you see emerging from these Bayesian models or from the neural network models, Don, that you mentioned before. They don't give you any insight. They just give you a bunch of numbers attached to nodes. And that's not an insight. That's not something that another theory can build on. Okay, now what about for the...
Okay, I just wanted to say, even though I'm not in the field of artificial intelligence, that I also can recommend people to go into this because all through the years, people working on artificial intelligence, from my point of view as an outsider, it has great value because you're working on a very hard problem, and because you're working on hard problems, you're going to build tools that people like me are also going to be able to use. Because in order to solve those problems, you're going to think of something that I wouldn't think of working on an easier problem. So
which is true, and it happened almost on day one with the invention of list processing languages.
Yeah.
No one set out to just invent list processing languages. They set out to do a certain kind of computation, and it was just horrendously difficult to do.
Yeah, without IPL5, I wouldn't, I wouldn't know how to solve all kinds of combinatorial problems.
And the other thing was McCarthy with his insight about time-sharing system. McCarthy was interested in seeing machines interact with people because that was in his artificial intelligence genes. That's what he wanted to do, and there had to be a way to do it. And he thought of time-sharing as a technique for doing that. So then I think for the people who are way out there, the 50 to 100 years from now people, this is a game. What I'm going to propose is a game that I'm not going to win and you're going to win because you're going to be alive and I'm not going to be alive. But it's the question of, will we have fully explicated the theory of thinking in the time of your lifetime, not my lifetime? Will all the questions be answered? Will we understand it? Will we understand all the processes that go on in the same way that physics strives to understand? When they talk about the standard model in quantum mechanics, they really mean that they've got it nailed. They've got virtually all the questions answered. Now, of course, there are mysteries and mysteries and mysteries below that, but It'd be very interesting to see what you people of 100 years from now know about all of this. 100 years is an enormous amount of time in scientific time. So what I do feel about computation is that we get into the habit, we have gotten into the habit of depending on exponential growth in the amount of computation, bang for the buck, that we get out of our computers. Once we're in this habit, we're not going to lose the habit. We may say that we're running out of gas on Moore's Law, but someone's going to find some other paths. Like, for example, recently we may have slowed down on the Moore's Law side, but we're doing faster than Moore's Law on the storage side. So, and we've traded off, we made some trades in the computation in favor of storage, and we're going to continue to do that. And so we're still going to have the amazing wonderland that we've had over the past few decades in computing. And now the question is conceptualizing. Are we going to be able to get the big picture right? And you guys will know, and we won't.
All right, well, too bad we can't be with you, but anyway, we wish you all the best.